after describing the synthesis of the elements of average mass, let us now examine the synthesis of heavy nuclides. At the moment of the explosion of the supernova, the heart of the star implodes and retracts on itself by gravitational effect. In this way, matter degenerates by compression, and is found in the form of an accumulation of planes of pentagons like a gigantic millefeuille. On the surface of the reduced star, these planes of pentagons, in direct contact with the galactic vacuum, will then be ejected by packets into space. And it is during these few weeks that the heavy elements are created before the neutron star constitutes an insulating shell. Consequently, each ejected pentagon packet will thus create an individualized nuclide in the manner of corn kernels becoming popcorn. And this nucleosynthesis is then extremely fast because the nuclide is instantly frozen as soon as it appears in the icy vacuum. By comparison, we have seen that the primordial synthesis of small nuclides such as hydrogen and deuterium took place in an expansive foam mode. Now we see that the popcorn synthesis of heavy elements is done in the spray mode. And in the galactic vacuum there are no external constraints such as internuclear shocks or destructive radiations as inside stars. These new atomic nuclei will then assume a spherical shape with gaps in the wall. And in the pentagonal structure, we have two obvious potential morphological bases, that is, the dodecahedron and the icosahedron. And these are the bases that we will now study. The dodecahedral morphological basis is presented under different layers. The first layer is organized on the association of 12 deuterium planes, which become hollow deuterium in a cup. The calculation of electric charge is simple because 6 external pentagons each give a unit of charge, and we therefore have a load of 12. Under these conditions, the first dodecahedral layer then has a unique representative, magnesium. With 10 pentagons in the crown around the base of the deuterium plane we get a larger cup. This structure of 6 times 16 pentagons can be associated with 6 planar deuterium to give the second dodecahedral layer. At the electric charge level we have a total of 132 external pentagons, and therefore 22 units. It is then the titanium element that is the unique example of the second layer. But with 12 times this base of 16 pentagons we get the third layer, where the wall begins to present 20 gaps at 6 sides. We then obtain a total of 192 external pentagons, and therefore an electrical charge of 32. It is element 32 or germanium. Then, with 5 new pentagons around this form 16, and thus a base of 21 pentagons in the cup, we have the fourth dodecahedral layer. The total of 252 external pentagons gives an electrical charge of 32 units. It is the molybdenum element with 20 parietal gaps of 12 sides, Finally, with 10 new pentagons based on 21, we reach the fifth dodecahedral layer with even wider gaps. We then obtain a set of 372 parietal pentagons, and therefore an electrical charge of 62. This is the samarium element with 20 gaps of 24 sides. We can now observe that the dodecahedral layers create 20 gaps from the third layer. And in the third layer these gaps have 6 sides. Under these conditions we have the possibility of introducing a group of 3 pentagons arranged in triangle in each of the gaps. Since these groups of 3 pentagons are included in the nuclear wall, they are involved in the electric charge count. Thus, with the addition of 2 groups of 3 pentagons, we have a new electric charge unit. Consequently, with 20 parietal gaps, the third dodecahedral layer generates 10 nuclear elements ranging from germanium at 32 electric charges up to molybdenum at 42. Now in the fourth dodecahedral layer we have wider gaps with 12 sides. Here again, each gap can receive a group of 6 pentagons arranged in a crown. As each addition of a ring of 6 pentagons gives a new electric charge unit, the fourth dodecahedral layer then supplies 20 nuclear elements ranging from molybdenum at 32 units to samarium with 62 charge units. With the fifth dodecahedral layer, the parietal gaps now have 24 sides. They are then too wide and too deformed to receive a complete regular crown. Under these conditions, each gap can receive only a maximum of 6 pentagons distributed around the circumference of the gap. We then obtain a sequence of 20 new elements ranging from samarium a charge of 62 to lead a charge of 82. It should be noted, however, that with the increasing complexity of the structures of elementary building blocks, the statistical probability of collecting them becomes increasingly weak to create heavier nuclear elements. This is why the constituent elements of the fifth layer are called rare earths. Now, since the number of nuclear isotopes is very important, we will give the general principles of their pentamorphic morphology without losing ourselves in the details in order to remain digesting in the context of this presentation.